Okay, welcome back to part 4 of this tutorial. In part 3, you would have seen that Dr. Chamberlain talked about using a compressed sensing approach to solve the coding problem for the multiple access channel. In this part, we're going to go back and take a largely a coding based approach to solving the problem. Nevertheless, you will see that compressed sensing has a role to play in these coding schemes as well. And what I would like to accomplish in this part is to first talk about a scheme called slotted ALOHA, which forms as the motivation for some of the work that we did. And slotted ALOHA itself was a scheme that was not originally designed for the Gaussian multiple access channel. So I will start with a review of this scheme and show you how to extend this scheme to the unsourced Gaussian multiple access channel, and then improve the scheme to result in what we call a sparse IDMA, which is the main point of this part of the tutorial. So before I go on with slotted ALOHA, I want to quickly review this MAC frame structure that we have talked about before, and just to keep the whole system in mind. So what we are really thinking is this: we have a bunch of K active devices that want to communicate to a base station. But the way the MAC protocol works is that the base station periodically sends a beacon. Now, if you are a device that has information to transmit, then you send a signature sequence or something to identify the fact that you are interested in transmitting, and that happens in this part of the protocol. Now, at the end of that protocol, or at that part of the protocol, the base station has identified who wants to transmit. And then the base station broadcasts a simple message saying, this is the number of people who have information to transmit. And then there is a frame length within which each of the users has to finish transmitting their code word. Now, keep in mind that the users do not know who else is there in the network. It's just that the base station knows who are there in the network, right? And this is why this is an uncoordinated transmission problem. And we're going to focus on what happens within this frame. Now, we're going to talk about 2 or 3 different schemes. In some of these schemes, we may want to cut this frame further down into slots, but eventually we may want to see that this is restrictive and we may want to relax this. So the point is that we are focusing on what's happening in this part of the slot of the frame. So coded slotted ALOHA is a coding scheme that focuses on trying to design codes for a channel where there is no Gaussian noise, but there is collisions from packets. Okay, so the idea here is this. The idea is you have a bunch of users. Let's say there are 4 users who want to transmit within that part of the frame I talked about in the previous slide. And we partition that frame into multiple slots. So for example, here, if you take this example, you have 5 slots. And what happens is each user chooses a random number and decides to transmit on that many slots within all the slots that are available. So for example, in this case, user M1 chooses a random number. The random number turns out to be 1. So user 1 randomly picks one slot between 1 and 5. It turns out to be slot 2. So user 1 transmits in slot 2. Now user 2 picks a random number. The random number turns out to be 3. And the user randomly picks 3 slots out of 5 slots. It turns out to be slot 1, 3, and 4. And the same thing happens for every user. And every user acts in a completely uncoordinated fashion. So they just choose their own random number and they pick these slots at random, which means there are going to be some slots where users are colliding with each other. And Leva and his co-authors came up with this very nice idea of trying to decode users in the presence of collisions by making a connection to decoding of codes and graphs. So for example, we can think of this multiple access problem as in terms of a bipartite graph. So we can think of a graph where we have variable nodes, which are the devices that are transmitting, and we have something like check nodes, which represent the slots where they have transmitted. And you can draw an edge between a device and a slot if that device repeated its information in that particular slot. So you can see that the graph that corresponds to this particular instance of the multiple access is given below. And you can see that device 2 transmits in slot 1, 3, and 4. Right? Now, the interference cancellation works as follows. So, and then just to remind you again, right now we're not thinking of any Gaussian noise. We're just focusing on collisions and interference in this part. And there is also no power constraint. So there is no penalty for somebody repeating their information many times. Okay, so then what we do is this. We look at the slots and see if there is a slot where only one user has transmitted. I mean, in practice, it may be something like you have a code at the physical layer for each of these packets. You try to decode, and if it decodes, then it means that you will be able to retrieve that information. But in this case, you can see that in slot 4, M2 is the only user who has transmitted. So you are able to decode M2. But once you have decoded M2, you can remove the contribution of M2 from the 2 other slots where M2 transmitted, namely slot 1 and slot 3 in this case. In terms of the graph, this amounts to removing the edges or peeling the edges off from the graph. Now, you go and look for another slot where only one person remains, or equivalently, you look for a node in the graph which has degree 1. If you find such a node, then it means that you can decode that particular device, which in this case is device 3. And then we remove the contribution of device 3 from slot 3 and slot 5. And then this proceeds in this way. And you can see that in this case, we can end up decoding all the 4 users or devices. So this is the basic idea of coded slotted ALOHA. It's a very elegant scheme which tries to, think about the problem as coding on graphs, and that permits us to use analysis techniques that we commonly know to analyze LDPC codes, to analyze the multiple access problem as well. And indeed, using these type of analysis, it turns out that you can design the probability mass function from which you should choose these random variables. This can be designed, and it turns out that you get very high throughput. In fact, we can prove that you can get arbitrarily close to 1 for the throughput, which means K users can more or less finish transmitting in K slots. So that was a very nice idea. But like I said, this does not consider Gaussian noise. So then what we did was to extend the scheme to the uncoordinated Gaussian multiple access. So at a high level, our scheme works like this. Now, it has a very similar structure to what you just saw, in the sense that every user is going to do some form of encoding, and they're going to repeat their information in a certain number of slots, and they're going to randomly pick slots within all the slots that are available. But we need to somehow design our code in a way that we can decode when you have either, let's say, only one person who transmitted in a slot or something equivalent to that. So we take a slightly more general approach here, and we say that we're going to design our code in such a way that if T or fewer users collide in a slot, we will be able to decode them. And then we will try to apply this iterative message passing or peeling decoder based idea. So the key thing we do here is this. So if you look at what each user does, each user's code word is constructed as follows. You should try to follow the picture above. So what happens is user's information is W. We first split this user's information into 2 parts. We split it into a preamble, which we call WP, and a part that needs to be coded, which we call WC. Now, what we do is this preamble selects a column of a sensing matrix. So we're going to try to transmit the preamble part using a compressed sensing type scheme. So this part is compressed sensing. And then this column from A forms the first part of the code word. Then we take the information, the second part of the information, WC, we encode it using an LDPC type code. It could be an LDPC code, could be a spatially coupled LDPC code, but for small lengths, more or less, we used LDPC codes. And then we permute either the graph in the LDPC code or the output or the code words using a permutation. This permutation is chosen based on the preamble. Okay. And the permuted version of the code word forms the second part of the code word. So the overall code word then contains two parts. There is a preamble, and then there is the coded part. Now notice that the preamble itself actually contains a part of the information, right? Okay. Now then what happens is the first part, namely the preamble, is also used to repeat this code word a few times across the slots. So for example, we get something like this. So you can see each person's information is split into two. The first part is communicated through through compressed sensing. The second part is encoded, and then you get the code word X1. And then X1 is repeated, but how often X1 is repeated is a function of the preamble part. Okay. Then every user acts like this in a completely uncoordinated fashion. If that happens, you might end up receiving a graph like this. Now, what we do at the decoder is that we go through each one of the slots and we try to see whether we can decode the slot, and the code that we chose here, this encoder, is chosen such that if two or fewer than two users transmit in a slot, we will be able to do the decoding. And one thing I want to remind you from my second part of the tutorial is that, remember when we talked about IDMA or spatially coupled LDPC codes for multiple access, I mentioned that it's important for the two users to do two different interleavers. And that's exactly the role played by this permutation here. So what you really want to do is we want to permute our code words, right? But we also want to somehow convey what permutation has been chosen to the receiver. And the way we do that is we make this permutation to be a function of the preamble. And then we're going to try to convey the preamble using a compressed sensing part. So if you look at what happens within this slot, the decoder first tries to decode the compressed sensing part here. If it successfully decodes the compressed sensing part, then it tries to decode up to two users in the rest of the part. And if it decodes the two users there, then essentially it gets the it gets the information, but also it knows, since the preamble is obtained, it knows that this code word was repeated in one more time slot here, and so we can go and peel that time slot off. So if you run through the peeling decoder, so you would decode W2, and then you remove W2 from the third slot. Now notice that third slot now can be decoded. Since there is only one user, we could have decoded, actually we could have decoded that even in the first round because there were only two users there. Now we can decode so pay attention to this particular user. This is the user that we cannot decode at this stage because there are three users here, right? Now this slot has only two users, so we can decode this slot. And once you have decoded these two users, we can remove one of the users from slot one, and now slot one has only two users, so we can decode these two slots. And this is basically the idea of what we called as a serial interference cancellation based scheme for the uncoded Gaussian multiple access channel. Now, T is, of course, a parameter. You can choose T to be 2 or 3. And here are some results based on this scheme. So this is the achievability bound that I talked about in the part 2 of Polyansky. And this is an early version of a coding scheme that was proposed by Polyansky and Ordentlich. And this scheme improves on this performance substantially. And as T increases, you can see the black curve corresponds to T equal to 1. T equal to 2 improves the performance from T equal to 1, which further improves as you go to T equal to 4. And the performance of the is reasonably good, but it kind of saturates when T is equal to 4 or 5. I think after the publication of this work, there is a recent work by Alexei Frolov, who replaced LDPC codes with polar codes, and I think they get much better performance than this as well. Okay, so once we did this, this is encouraging, but we still have somewhat of a gap from the achievability part, and what I'm going to talk about next tries to bridge this gap. And to try to bridge that gap, let's try to understand what are some potential limitations of this scheme that I just described. So if you think about this scheme, there are two problems with the scheme. The first one comes from the fact that we are trying to cut the frame down into a bunch of smaller slots. So that necessarily means that we have a small number of channel users to code over. And so the finite block length bound starts to become a limiting factor. Secondly, if you notice, we repeated our packets multiple times. Like some users repeated their packets multiple times, right? But those multiple copies were not really used in the decoding of the packet. The only thing that we did with the multiple copies was to increase your chance that you find yourself in a slot which can be decoded, but then the rest of the copies were actually peeled off. And both these, as you can see, are somewhat limiting, and our next proposal tries to fix this, and that's exactly what I want to talk about next. And this is called as sparse IDMA. Okay, the key idea in okay, I'm gonna give me a minute here. I'm gonna check to make sure my recording is okay. Yeah, I think it's still recording. Okay, so the idea in sparse IDMA is to say we don't want to have slots. We don't want to cut the frame into slots. Rather, what we want to do is we want each user to use all the time slots that are available. So if you look at all the time or all the channel users that are available, it's better to use the word channel users because we don't really have slots anymore. But if we try to do that, and indeed what we tried at first was to say, okay, let's just use IDMA, let's just take a code, we encode it, and then we'll use an interleaver and we'll try to use all the slots. But it turns out it becomes very hard to design your codes for this system to work well. And to circumvent this problem, what we did was to sparsify our transmissions. So the scheme in the end works like this. Just like what we had in the past scheme, we start with W, which has two parts, is a WP and a WC. And we convey the preamble part through a compressed sensing, just like what we did before, and that forms the first part of the code word. Now, the second part of the information, WC, is encoded by a channel encoder, just like what we did before. And we take the output of the channel code, we repeat the bits instead of the entire code word. Okay, actually you can think of it as repeating the entire code word also. We repeat it by a function that depends on the preamble part of the message. But then we permute the coded bits throughout the entire frame that's available. So for example, if you think about it, each one of these little blocks here corresponds to a coded bit. This coded bit is perhaps repeated, but then it is interleaved, or it occupies the entire number of channel users that are available for us in the frame. And each user does this independently. If you do that, you're going to get a slot structure that looks like this picture here. The first part in everybody's transmission is the compress sensing part, where everybody tries to convey the interleaver that they are choosing. And then in the other part, we are actually transmitting coded bits. But here you see, because we use this interleaver, we necessarily sparsify these transmissions. And this sparsification turns out to be a really important improvement compared to what we had before. In particular, notice that if I pick a time slot, so for example, if I pick this time slot, there are 2 users who transmit in this time slot. But if I pick this time slot, I have only 1 user who transmits, whereas in this time slot, there are 3 users who transmit. So in general, since the users are not coordinated, what's going to happen is if I pick a time slot at random, you're going to have a number of users, which is a random variable, and that random variable is going to have a Poisson distribution. Let's just keep that in mind as we go through. Okay, then the decoding works as follows. So instead of decoding a small number of users like in the past, we're going to try to decode all the users together using a joint Tanner graph. And I'm going to show you an example here with 2 users, but the same idea extends to multiple users as well. So you can see that the structure of the code that we get can be very nicely described using the Tanner graph here. So what we are showing here is this is user 1, this is user 2. These are the coded bits of user 1. These are the check nodes for user 1. These are nodes which we call as repetition nodes, which tell you how many times the coded bits have been repeated. They're all permuted, and then they're transmitted through a multiple access channel. So if 2 users transmit in a particular channel, then you're going to observe the sum of what was transmitted in them. And keep in mind, how often we repeat and how we interleave depend on the first part or the preamble part of the message. Okay, now I'm going to walk you through the steps in the message passing decoding for this. So first, let's look at what happens at what we call as the MAC node. Again, there are 4 kinds of nodes here. This is what I'm going to call as a multiple access node. This we can call as a repetition node or as a repeat node. This is a variable node or a coded bit. And this is a check node in my LDPC code. So at a MAC and throughout the next few slides, we're going to have incoming and outgoing messages on every node. The incoming messages are colored in blue and the outgoing messages are colored in red. So if you think about a MAC node here, so let's look at this 5th MAC node. The MAC node observes Y5 at the output of the channel. And what the MAC node gets is it gets a log likelihood ratio from the 2 users. So let's focus on the log likelihood ratio that is incoming from the second user. And let's think about the log likelihood ratio that we should send to the first user from this node. So what we do is this: we form a soft estimate of this bit based on this log likelihood ratio. So the M's are log likelihood ratios. The soft estimate of this bit is given by the hyperbolic tangent of that log likelihood ratio divided by 2. Now we remove the soft estimate from Y5, and now the soft estimate is not perfect. So when we try to make an estimate of this bit from the log likelihood ratio, we're going to have some mean squared error in that estimate. That mean squared error is given by 1 minus tan h of the log likelihood ratio over 2 whole squared. Now, remember, this is an error in the estimate of this bit. On top of that, we have some variance in the channel noise. So as a result, the uncertainty we have about this bit, the variance of that is the sum of the two variances, and that's exactly what you see in the denominator. And if I had no interference, if you look at a node where only 1% transmitted, then the log likelihood ratio would simply be the log likelihood ratio that you would get at the output of an additive white Gaussian noise channel, which is 2 times the log likelihood ratio divided by sigma squared. Now, I'm not sure how many of you have seen these kinds of things before in coding, but these are somewhat standard in coding. The fact that you have a log likelihood ratio, which is 2 times what you observe by sigma squared. If you have not seen this before, it might feel a little bit like, where is this thing coming from? I suggest that you read a few papers in this area to be able to see where that comes from. And then the next thing that happens is processing at the repeat node. At the repeat node, we get 2 incoming messages, or in this case, you get 2 incoming messages, and you have 1 outgoing message, but that outgoing message is simply the sum of all the incoming messages. And then we look at what happens at a variable node. So a variable node gets some message from the repeat node, it gets some message from the check node, and it has to add these log likelihood ratios to send the message on the outgoing edge. And that's indeed what happens. It happens here as well as here. And finally, or the next thing we do is we look at the outgoing message from a check node. So the check node has incoming messages from the variable nodes, and it sends an outgoing message to a variable node. Again, when you use the rules of message passing, you can see that this message should be given by 2 times the inverse hyperbolic tangent or the product of the hyperbolic tangent of the incoming messages over 2. Again, this is a fairly standard message passing rule. And then this propagates downwards, just like what we did before, and that completes 1 iteration. Now, that's basically what the message passing is doing, and it's doing this for every user simultaneously. Now comes the next question of saying, okay, how should we design our codes? Now I talked about having a Tanner graph for a code, right? But how did we actually get this Tanner graph, or how did we design this Tanner graph? Now it turns out that if you simply pick a code that is optimized for the single user channel, it turns out to be not a good idea. It does not really perform very well. We need to optimize the irregularity in these LDPC codes, or the degree profile for the LDPC codes, to be tailored to this iterative decoding algorithm. And what we do is we picked a class of LDPC codes called as Protograph LDPC codes. A Protograph code, without going into too much detail, has a very small graph that shows connections between the variable nodes and the check nodes in a Protograph. And the overall LDPC code is obtained by making several copies of this Protograph and then just interleaving the 12 different kinds of edges that you have here. So you can see there are 12 different kinds of edges. You make many copies of this and then just permute each edge class within itself. Now the question then is, how should we design this Protograph? And the way we did it is to use what is by now somewhat of a standard procedure in iterative decoding, which is to track the mutual information that corresponds to these various messages that we are passing, and to optimize the Protograph degree profile using an optimization technique. I'm not going to go into too much of the details about this. So this procedure that tracks the mutual information is known as density evolution. I'm not going to go into too much of the details because many of this is fairly standard in the analysis of LDPC codes. The only thing that is not that's not something that you see that often is what happens at the MAC node. So I will just quickly walk you through what happens at the MAC node. Again, just to jog your memory, again, keep in mind that if I pick a MAC node at random, the number of users who transmit in that slot is going to have a Poisson distribution. So then we can track the mutual information that goes from a MAC node to the repeat node as follows. So let's take an example. Let's say we have a MAC node that corresponds to the sum of 2 repeat nodes, X1 and X2. Now, what we do is we observe Y at the MAC node, right? Let's say that this is an incoming message from one of the repeat nodes. And we want to find what is the mutual information between the repeat node X2 and the message that this MAC node sends to that repeat node. In other words, how informative is the message that you are going to get out of the MAC node? And to compute that, what we do is we first look at the interference cancellation, right? We're going to remove the soft estimate of X1 from Y. And whatever is left, we're going to think of this as our estimate for X2, right? But we're going to model this information as though there is an underlying channel. So it's like saying what the MAC node is sending to X2 is that it's giving some information about X2. But you can think of that information as the MMSE estimate that you get about X2 if X2 were passed over an equivalent Gaussian channel. Now the question then, of course, is what is the variance of the noise in that Gaussian channel? And that we call by sigma I squared. And we can compute this sigma I squared by computing the variance of this estimate here. So to do this, you need to evaluate a function. So essentially what it is you say that if my M1 has a Gaussian distribution, I assume that M1 has a Gaussian distribution with a mean of sigma M1 squared over 2 and a variance of sigma M1 squared, then I can remove tan h of M1 over 2, and then I will be left with X2, and I can compute the MMSE estimate, the error in the MMSE estimate of my M1. I can add that to the error that I would get from the channel, and in the end, we can get the error in the MMSE estimate for X2. And once you have this equivalent variance, then you can say that we can compute the mutual information between the message and the bit itself. And this is computed by using this function called J. So finally, the mutual information that goes from the MAC node to the repeat node has a simple form. It is this function J. Of course, J is a function you have to numerically evaluate, and we'll put some papers on a website where our paper has exactly the form of this function J. Okay. Now this happens at a check node of degree 2, but remember there are many. A MAC node of degree 2. But remember, there are MAC nodes of many different degrees. And so if you pick an edge that comes out of a MAC node at random, it's going to be connected to a MAC node of degree k with probability gamma k. And therefore, the mutual information that comes out from a randomly chosen edge from the MAC node should be the weighted average weighted by the Poisson distribution. And that's exactly the final mutual information that comes from the MAC node to a variable node. Now, once we have this expression, what we do is what we would like is this. We would like to track this mutual information that corresponds to all the messages, from the MAC node to the variable node to the MAC node, variable node to the check node to the variable node, and there should be something where we have the variable node to the repeat node as well. And we track it as a function of iterations, and we want to find the minimum signal to noise ratio for which the mutual informations go to 1, which means we have decoded everything perfectly. And then we use an optimization procedure to optimize the protograph such that we minimize the signal to noise ratio for this to happen. And it turns out that the rate that you choose for each of the LDPC cores, remember, this is a parameter under your control, right? You can choose whatever rate that we want to choose, and we can choose whatever repetition factor that we want to choose. It turns out that you have to be careful to choose this, particularly as the number of active users decreases, you want to decrease the rate that you choose, and as the number of active users increases, you want to increase that rate. And when we optimize this, here is the result we get. Remember, I just showed you the result for serial interference cancellation with t equal to 4. That was in the last slide. Now, in the earlier parts, you may have seen results for coded compressed sensing. And this is the result for approximate message passing with the tree code. Now, we didn't show the performance. I also talked about this polar code, right? We talked about this polar code replacing the LDPC code in our ALOHA scheme. And then the sparse IDMA performs like this. You can see that this is a big improvement going from this interference cancellation. So that's what you gain by getting rid of the slot structure and by sparsifying your collisions. And I think I'm going to stop here. And in the next part, I'm going to talk about a different way to improve on this performance. I'll see you back soon.